Yeah, welcome to my talk about the Skyrmion-based rotation countersensor device. My name is Kilian Leutner. I'm a PhD student at the Johannes Gutenberg University Mainz, and my supervisors are Professor Kloyi and Professor Fangerer from Hamburg and Southampton. Now, why are rotation countersensor devices interesting? Because they're diverse application and there is a large demand for them. Because, for example, application is this conveyor belt. There you have an axle, and you can, and then you want to count the number of revolutions. Or here in such robot arms, you have also several of these rotation countersensor devices. Now, for counting, you can use particles, and as particles, you can use skyrmions, which are quasi-particle spin textures, which are topologically stabilized, especially due to the Chia-Lucy-Moria interaction, but there are also other interactions which are important, like the stray field interaction. Now, the idea now to build such an skyrmion-based rotation countersensor device out of skyrmions is the following. You have here, for example, an axle from your conveyor belt, and then you attach a permanent magnet. Here again, this axle with the attached permanent magnet. Below, you place then a soft ferromagnetic ring, which has here two domain walls, which have a sizable stray field. Beside of the soft ferromagnetic ring, you place then a ferromagnet which hosts skyrmions. Now, when you rotate this axis, you also rotate the stray field, and when this stray field passes through with the in-plane component of the stray field, it will nucleate a skyrmion, because this ferromagnet also can host skyrmions. So that means for each 180-degree rotation, you can nucleate one skyrmion. That means you can sense 180-degree rotations without any electrical power consumptions. Afterwards, you store then your skyrmions here in the reservoir, so the number of 180-degree rotations. Now you have to move them out of the nucleation area unless you do via skyrmion automotion. This I will explain in my talk. Also, during the storing, you don't need any electrical power consumption, only at the end where you apply then a current for the readout with the empty chain. Afterwards, this current get annihilated. And only here you need electrical power consumption. Now, the large advantage of this concept are two things. The first is you don't need an electrical power consumption during sensing and storing, and only during readout. This is very good for safety and reliability, but the large advantage compared to other concepts which also have not electrical power consumption during the sensing and storing is that here you can make this reservoir almost arbitrarily large, and this way count a relative large number of skyrmions before you have to read out. And this large number of counting before read out is not given in other concepts. Now, in my presentation, I will now show you simulations of critical parts of the sensor and show you that this is a viability to build this sensor. But before, a short comment about the experiment, the simulation I use, and the skyrmions in the experiment. So in the experiment, we use micrometer skyrmions, which are visible to the Kerr microscope. On the other hand, in the simulation, I use nanometer skyrmions because they're computationally efficient. Now, for the experimental skyrmions, for example, we use this multi-layer stack with this Fourier temperature at 450 Kelvin with a small external field. The radius is around 1 micrometer. The lifetime at room temperature is about 10 years. And then you calculate over 1 second at 300 Kelvin, the mean square displacement, and you from this to square root, you get 1 micrometer. And when you compare it to the radius, you see you have significant diffusion. On the other hand, for the simulation, I use this palladium iron on iridium with this 214 Kelvin Fourier temperature and this relatively strong external field. And they have only a radius of 2 nanometers. So at 15 Kelvin, they are more or less only stable for some milliseconds. At 5 Kelvin, they are long-term stable. And when you calculate also here the mean square displacement of 1 nanosecond at 5 Kelvin, and at the square root you get 1 nanometer. When you compare it to the radius, you see also here you have a significant diffusion, and this is good. So we can also simulate this diffusion and thermal effects with this relative small skyrmions at 5 Kelvin. So now the first part is the skyrmion automotion. So when you have your ferromagnetic ring, you can then here nucleate with your stray field skyrmion. So here again, you have nucleated skyrmion, and then the skyrmion will move automatically out of the triangle into the reservoir without any external energy, and this is only due to the skyrmion boundary force. And you could do this for different positions, and always the skyrmion will move out of this triangle in this clockwise manner, and then you can calculate the escape time for each position, and you see here the escape time is long. Relative interesting is this position, because here there is a large distance to the reservoir. This is good because then the nucleation stray field will not influence your reservoir, but since the escape time is slow, it's coming really relatively fast, moves out of the reservoir, out of the triangle into the reservoir, and therefore it is free for the next nucleation, for the next rotation. And this also works reliably in the in multi-layer stacks, where, for example, with where you have multiple repetitions, and the force of the Skyrmion boundary interaction scales then with the number of repetitions. Now, when we go to temperature, because for it was on a 0 Kelvin, then we have thermal diffusion of the Skyrmion. But even then, in this case, you see the this automotion works also when it has here some diffusion. And we showed in our paper systematically that also in the presence of thermal diffusion, you can also in the presence of thermal diffusion, you can this Skyrmion automotion works. Afterwards, you have your storage of your Skyrmion. This works perfectly in these multi-layer stacks. At room temperature, they are over 10 years stable, so this is all fine. So the next part is then the readout of the Skyrmion reservoir. So here again, you apply here the current to detect the Skyrmions. Then here move the Skyrmions under the MTJ. The MTJ detects them, and afterwards they get annihilated. Now, when you look in literature, you find a lot of simulation of the Skyrmion-based deterministic operating devices. With deterministic operating devices, I mean not devices like reservoir computing, where you use explicitly the stochastic nature, but in these deterministic operating devices, the literature is to the majority focused on the 0 Kelvin. However, even in this deterministic case, there are additional challenges which emerge at a non-0 Kelvin, and you inherit also the problems from 0 Kelvin. So one problem is that you don't want to have a Skyrmion annihilation at the boundary. Here at the boundary, you don't want annihilation at the boundary because you want to count them. But after the detection, you want to mandatory annihilate them because you need a unique signal to know the number of Skyrmions. On the other hand, you need an appropriate current density. When the current density is too high, then the Skyrmions will annihilate at the boundary. When the current density is too low, then they will not move here into this racetrack because there is a Skyrmion boundary force, and the Skyrmion will not move in. Additionally, you need a unique electrical signal. Also in the presence of thermal diffusion, because the Skyrmion could go under the MTJ and go back in the reservoir, and this is also a challenge. Additionally, you need a sufficient signal-to-noise ratio, because due to the thermal fluctuation, you need some mechanism to also then work reliably. So we found a design which solves all these problems. We used there for the simulation, again, the nanometer Skyrmions at 5 Kelvin, and we simulated this with Mumax and Phoenix, and this yielded the required components. So here you have your sample with here your current contacts. Then the first thing is you have here a smooth boundary, because then you don't have annihilation of Skyrmions at the boundary because it's smooth. Additionally, you have here a triangular notch, because with this you can annihilate the Skyrmions. Additionally, we optimize the Skyrmion position so that first the Skyrmion is detected and afterwards immediately destroyed, because you have also here the current which pushes the Skyrmion in this direction. However, additionally, we introduced here an anisotropy gradient, and this leads to a strong force on the Skyrmion, and this you can also experimentally realize with irradiation. Now, the advantage of this is due to the fact that due to diffusion, the Skyrmion could move back into the reservoir, but now to the strong anisotropy gradient makes a strong force, so the likelihood is very, very low that the Skyrmion moves back into the reservoir through the diffusion, and it gets reliably destroyed. Now, additionally, we have also a readout protocol. Let's see how to do this, how to read out. So first we start here with a relative small current density, and then you see the Skyrmion moves here, and then they under the MTJ, and afterwards they can annihilate. Now we simplified here a little bit the readout. We looked here at in this area at the spatially average set component of the reduced magnetization. When this quantity is under this threshold, we set here a state to 1. When this is again over an upper threshold, we set the state again to 0. For each falling edge, we added then 1 1 to the number of the counted skyrmions, and we check this also with the topological chart. So this works. But now in the reservoir, the skyrmions interaction decreases because you have less skyrmions. On the other hand, you have also here skyrmion boundary force. Then the skyrmion will not move here anymore towards this readout position. Therefore, we also monitor the time since the last skyrmion detection, and when this time is over 10 seconds, then we increase here again the current density. And then you see here we have then increased current density, and then it's high enough. So we validated our concept. We did in total 25 micrometric simulation, each with 50 skyrmions, and we could successfully validate our without concept. Now the thing is, now let's push this again to the top. The thing is, we always need one current increase to read out all the skyrmions. But in 37% of the cases, this is enough, and you can read out the full reservoir. But in the other rest cases, you need, in the other 60 or 70% cases, you need a second current increase to read out all the skyrmions. But you see with the overlap of the total time of the readout process that more or less after you have the second current increase, shortly after this, all the skyrmions are read out. And you see here also a peak in this total time here at lower times than this the case, because you have in 37% of the cases, one current increase is enough. And the current increase is made with this formula. Now let's conclude. There is on top only the conclusion and the title again, current-based rotation counters and survey mass. Now the thing is, so here you can find all the necessary information when you want to have all the details. Then no, it's again here. Then here we only to conclude, only the readout requires electrical energy consumption. You can sense almost an arbitrary large number of revolutions because you can scale up the reservoir, and this makes it a better concept than other one, because you can scale up the reservoir and count then a lot of revolutions before the readout. And we verified also the aspect of the sensor with simulation that I showed you in this talk. And the outlook is we currently experimentally implement this sensor in cooperation with Infineon, and also these concepts which I showed to you are generalizable to other readout to other skyrmion devices. So at the end, what I want to acknowledge my collaborators and funding agencies, and thank you very much for your attention.
So thank you, Kilian, for your very nice presentation. Nice figures and videos. So we are now short in time, except if there is like very, very quick questions, we can take it. Otherwise, you can meet Kilian directly in the Gather Town. So Kilian, you can also like be present in the Gather Town, so you can receive other questions. So thank you again for this presentation.